Dudes, so I'm so interested in these waves coming from the Fourier series. Please bring them. Let me see some real waves so we can get all gnarly and tubular. Yeah. Yes, we can do that. Let's do it.
This is exercise 4.1.7. So the idea is let f of x be 1 if negative pi is less than or equal to x is less than or equal to 0, and 0 if it's on the other part of the interval. So, it looks like this. And so it's right there. I guess I probably need to put that there. Yeah. That's the function. And part A is show that the Fourier series of f is 1/2 plus 1 over pi summation n equals 1 to infinity of negative 1 to the n minus 1 over n sine of nx. So let's do the proof of that. Well, just compute. So f of x is going to be some constant, maybe b0 plus summation of bk cosine of kx. K equals 1 to infinity and then over square root of pi. And this is over square root of 2 pi. These are the constants times the vectors of the orthonormal basis. And let's see, when we do m equals 1 to infinity of cm sine of 1x. There we go. That's what we're looking for. So b0 is going to be the inner product of f with 1 over square root of 2 pi, which, if you plug that in, we're just going to integrate from negative pi to 0 of 1 over square root of 2 pi times itself and dx, and that'll be the inner product. These are both real. Don't have to worry about complex conjugates. And let's see, so yeah, got that right. Great. And so it's just a constant times pi. Okay, so note then that b0 over square root of 2 pi would equal 1 over square root of 2 pi times 1 over square root of 2 pi equals 1/2. Okay, great. And now let's calculate the bk's. So those will be the inner product of f with cosine of kx over square root of pi. So let's see, again, it's just going to be integrating negative pi to 0 of cosine of kx over square root of pi dx. And notice that this makes a cycle over here. Like for 1x, it would be like that. 2x, it would be twice as fast. But the integrals can be 0. It just tells. So that's cool. And then the last one is the CMs, or the product between f and this function. So let's see, it's the integral from negative pi to 0 of sine of mx over square root of pi dx. Okay, sine's going to be negative over here, so we need to actually do this calculation. And so we get 1 over square root of pi, and then over m with a negative times cosine of mx. I believe that's right. Take the derivative, yeah, you get that. And we go between negative pi and 0. So you get negative 1 over m squared of pi, plugging in 0, and then cosine of negative m pi is the same thing as negative 1 to the m. So that would be minus negative 1 to the m. Make sure I got that right. Oh, it would be a plus, because that would be right there, and over m squared pi. So it equals negative 1 to the m minus 1 over m squared pi. And so then that one's 0, that one's 1/2. So we get that the Fourier series is equal to 1/2 plus sum from n equals 1 to infinity of this thing, negative 1 to the m, minus 1 over m squared pi. The cosine terms are 0, and then we multiply times sine of mx over square root of pi. So it equals 1/2 plus sum m equals 1 to infinity of negative 1 to the m minus 1 over m pi sine of mx. And notice it's exactly what we have here. Great. There's the Fourier series. Yeah, by the way, you can verify this by going to Desmos and graphing a partial sum of the Fourier series and see if it looks right. And let's see. So it should look, this should look like this function looks like that. So let's just kind of graph it plus, let's see, sum from n equals 1 to maybe do 5 to start out with. And then we'll put negative 1 to the n, oops, n, minus 1, and the whole thing divided by n pi, and then times sine of nx. And look at that, we're going from negative pi to pi, so it's looking pretty close. We can change that to maybe 10 terms. Gets closer. Ooh, let's do like 40 terms. Gets closer, 100 maybe. Looks almost exact to the function we were finding the Fourier series of. So we did a great job with that example. Yeah. All right, let's go back to the work we're doing. Okay, and actually that was only part A of the question. Part B is why does this converge to this? Converge to F. Well, let's see. So it should be true that if we take F minus the nth partial sum and take the inner product norm squared, that should be going to 0. So let's just see what we would get. All right, so it would be the integral from the function minus that. Well, that'll give you a 1/2 of negative pi to 0, and then it won't do anything except the minus the sum on the second part. And then minus this sum, m equals 1 to infinity of negative 1 to the n minus 1 over n pi sine of mx. We know it converges because of, well, the Reese-Fisher theorem, which we haven't proved yet, but anyway. Let's see, and then we're going to integrate that dx, and then plus the part from 0 to pi, where we just subtract that off, and then with that it's a negative. So negative 1/2 minus summation plus 1 to infinity of negative 1 minus 1 over pi sine of mx dx. Oh, and then, yeah, we're only going up to the nth term, so the infinity term. And we want to show that actually goes to 0. So let's see. Okay, so the first term, so first of all, this part and this part will cancel because that'll give you 1/2 times pi. That'll give you -1/2 times pi, so those will cancel. And then these two parts will add. So we can just put that all into 1. So we get that f minus sm norm squared is, oh, I forgot to put squared. Okay. Well, in that case, it's not quite so simple. The 1/4 term will cancel, but then there'll be something weird with the cross term, and then this term squared we can do on both. But, okay. So let's look at that more carefully. So we get negative pi to pi 0 of 1/4, and then minus 2 times that, so that'd be minus summation n equals 1 to infinity, and -1 to the n minus 1 over n pi sine of mx. That's the cross term, and then plus the last term squared plus summation equals 1 to infinity of -1 to the n minus 1 over n pi sine of mx. That thing is squared dx, and then plus pi to pi. Alright, so 0 to pi. Okay, so now it's going to be that. So that will be a 1, let's see, so it would be that thing squared. And so that'd be 1/4 again. And then that would be plus summation n equal 1 to infinity of -1 to the n minus 1 over pi sine of mx. A cross term. And then plus the same thing squared. Yes. Alright. So simplified, that'll give us 1/4 pi, that'll give us 1/4 pi, so we get 1 over 2 pi, or 1/2 times pi for that part. And then we'll just have to figure this out. Let's see. This is going to be a minus with that, you're going from negative unit and that, and that'll be a plus. So actually, when you integrate it, you're just going to get 2 times this one, because when sine of negative x is the same thing as sine of x. So this part and this part will be just 2 times this part. So it'll be 2 times from 0 to pi of summation n equals 1 to infinity of -1 to the n minus 1 over n pi sine of mx. And then let's see, this thing is going to go all the way to 2 pi. That's going to go from negative pi to pi of that. And we're only going to the nth term. I keep putting infinity. Yeah. Alright, so let's, this one right here, if we go from 0 to pi, it's going to give us 2 times -1 to the n minus 1 over n pi. And then it'll be cosine of mx, negative cosine over n from 0 to pi. Okay, and work out that later. Yeah. Okay. And then plus this one, that's the inner product with that with itself. And notice the only terms that will occur are where it's sine squared and mx. If it's 2 different ones, they'll be orthogonal, so it'll give you 0. So sine squared is going to give you 1/2 times 2 pi, which is pi, integrated out. So we can actually just compute this. And then it's going to be that term squared, so it's going to be sum n equals 1 to n of -1 to the n minus 1 over n pi n minus 1. That thing squared times pi. Okay, now let's put that one in there. Yeah, I forgot the sum. And so you get pi over 2 plus sum to -1 to the n minus 1 over m pi. And let's see, put pi in, that'll be minus -1 to the m over m. And then plugging in 0 plus 1. Good. So notice that's just exactly the negative of that. So it'd be negative that squared. And let's see, yeah. And I'm going to go ahead and multiply that by that. This squared over m squared pi. One of the pi's cancels. Okay. And this will be, let's see. -2, and then there's a pi in the bottom, and -1 to the m minus 1 squared over m squared. Okay, so notice this part cancels with that part, except for there's a 1 over pi here, a 2 over pi here. So the whole thing is equal to pi over 2 minus 1 over pi times summation of -1 to the m minus 1 squared over m squared. Yeah. Now, notice that, and this is n equals 1 to n, like that. Now notice that this guy right here is, it's, if m is odd, it's -1, and if it's even, it's +1, will cancel. So it's actually the sum up to n of, and then when it's odd, it will give you -2 squared, which is 4 over n squared. And then as n goes to infinity, we get sum from m odd to n of 1 over m squared. And that's one of those you can look up. It actually comes from a Fourier series, and you can actually find it. So, so that has to converge to 0. But anyway, we already know, because the Fourier series is a complete orthonormal basis, this has to go to 0. So in fact, it gives us that those two things have to equal, and so they get 0, and so we get 1 over pi times summation of m odd to infinity of, I can pull the 4 out, 1 over m squared equals pi over 2. So that tells us that the sum of m odd of 1 over n squared equals pi squared over 8. That's a kind of nifty formula that comes out of that Fourier series calculation. All right, now let's look at question C. So actually B, we know it converges since the Fourier series basis is a complete orthonormal basis of L2 of negative pi to pi. And we also get this nifty formula for the sum of the odd squares. We can kind of check that later, but anyway, part C is, let's see, what's the question? Does the series converge pointwise? Uniformly? Well, if it converged uniformly, it would also converge pointwise. So, and it turns out it does not converge. Well, it actually does converge pointwise, but not at particular points. So the first question is no, because notice at when x is, say, 0, the Fourier series, the function f of x equals 0. 1 actually, yeah. But the Fourier series equals 1/2 plus 1 over pi, sum of a bunch of sines of zeros, so it equals 1/2. So in fact, that's not equal to 1, so it does not converge pointwise. It actually does at every other point. And which also implies that it does not converge uniformly. Because every partial sum is a continuous function, and a uniform limit of continuous functions is continuous. So it can't converge uniformly. Okay. And then the last question is, why are the cosine coefficients all 0? Well, if you look at the original function, it looks like this. Here's negative pi, here's pi. And that's f of x. And then if you look at f of x minus 1/2, which is that first term, it is an odd function. And so that tells you that the integral of f of x minus 1/2 with any cosine of mx dx from negative pi to pi will be 0, because then that's an even function, that's an odd function, so that's an odd function. And so it will cancel to be 0. So therefore all cosine terms are 0. Yeah. Before I leave this example, I did want to check our amazing formula we got in the first part. Let's look at it. So it's sum of m odd is pi squared over 8. So I'm going to whip out a program here, and let's compute it. So let's go for the odd numbers, so let's go from k equals 1 to maybe the first 20 of them, and we'll calculate 1 over 2k minus 1 squared. Okay, good. Now let's maybe go farther. 50. Okay, maybe let's do 200. We do 500. See what happens. Okay, so we're getting, it looks like it's converging. Let's see what pi squared over 8 is. Look at that. So it does seem to be converting to that. So that's a nifty formula that I don't know of another easy way to derive that, but we got that from our Fourier series calculation. Pretty cool stuff. All right. See you later for the next example.